Welcome, cosmic travelers, to the far reaches of our solar system. Out here, where the sun is just a bright star, spins a majestic blue giant. This is Neptune, the eighth and most distant planet from our sun. It's a world of extreme cold, supersonic winds and deep, deep blue clouds. Neptune wasn't discovered by someone gazing through a telescope by chance. Its existence was predicted by mathematics before it was ever seen. Scientists noticed that Uranus, its planetary neighbor, was not quite following its expected path. Something unseen was tugging on it. That something turned out to be Neptune, a gravitational whisper from the darkness. This makes Neptune special. It's a testament to the power of scientific theory and the invisible force of gravity. Neptune is the king of its own mini-system, complete with a fascinating collection of moons. As of my last check, we know of 14 moons orbiting Neptune. Each one has its own story, its own peculiar characteristics. By exploring this distant realm, we learn not just about Neptune itself but about the processes that shaped all the planets, including our own Earth. So, let's embark on this journey to understand how this blue giant acquired its diverse family of natural satellites. Before we dive into Neptune's specific lunar family, let's talk about how planets usually get their moons. There are a few standard ways this happens in the universe. The most common way, especially for the giant planets like Jupiter and Saturn, is that moons form from a disk of gas and dust that surrounds the young planet. This is very similar to how the planets themselves formed around the young sun, a sort of mini solar system in the making. Dust particles collide and stick together, growing larger and larger over time. First they form small clumps, then bigger ones, eventually becoming moonlets. These moonlets continue to sweep up material, or they merge with other moonlets until they become full-fledged moons. Moons formed this way tend to orbit in the same direction as the planet rotates. They also typically orbit around the planet's equator, forming a neat, orderly system. Another way a planet can get a moon is through a giant impact. This is how Earth likely got its moon. Imagine a massive object, perhaps the size of Mars, slamming into a young planet. The collision would be catastrophic, sending a huge amount of debris blasting out into space. This ejected material would then go into orbit around the planet. Over time, gravity would pull this debris together, and it would coalesce to form a moon. Now let's zoom in on Neptune's largest moon, Triton. This moon is a true giant, one of the largest in our solar system, even bigger than the dwarf planet Pluto. Triton is an incredibly cold world, with surface temperatures plummeting to around -235 degrees Celsius. Its surface is a fascinating landscape of icy plains, frozen nitrogen and geysers that erupt plumes of icy material high into its thin atmosphere. What makes Triton truly stand out, however, is its orbit. Triton orbits Neptune backwards. That is, it travels in the opposite direction to Neptune's rotation. This is a huge red flag in the world of moon formation. Triton's retrograde orbit is a clear sign that it wasn't born alongside Neptune. It's an outsider, a captured object from somewhere else in the solar system. Scientists are pretty confident that Triton was once a denizen of the Kuiper Belt. The Kuiper Belt is a vast, icy region beyond Neptune, home to countless comets and dwarf planets like Pluto. Triton, the rebel, reshaped an entire system. While Triton is the big, rebellious star of Neptune's moon show, there's another moon that raises eyebrows with its peculiar behavior, Nereid. Discovered way back in 1949 by Gerard Kuiper, Nereid is much smaller than Triton. But what it lacks in size, it makes up for in orbital weirdness. Nereid has one of the most eccentric orbits of any moon in our entire solar system. This means its path around Neptune is incredibly stretched out, like a very long, thin oval. Nereid swings incredibly far out from Neptune and then comes incredibly close. At its farthest point, it's about 9.6 million kilometers from Neptune. At its closest, it's only about 1.4 million kilometers away. This highly elongated orbit is a strong indicator that Nereid, like Triton, is probably a captured object, rather than one that formed alongside Neptune from a primordial disk. The story of Nereid's capture is likely linked to the dramatic arrival of Triton. When Triton was captured, its immense gravity would have thrown Neptune's original moon system into chaos. Nereid might be a survivor, albeit a heavily scarred one, from Neptune's earlier, more orderly family. Nereid remains a bit of an enigma, a testament to the complex and sometimes violent gravitational interactions that shape planetary systems over billions of years. Section 5, Cosmic Kidnapping, How Neptune Snatched Its Moons. So, how exactly does a giant planet like Neptune kidnap a moon like Triton or Nereid? It's not like Neptune has a giant cosmic hand to reach out and grab things. The process relies on the subtle yet immensely powerful force of gravity, and often a bit of cosmic luck or a helpful third party. Capturing a free-roaming object into a stable orbit is actually quite tricky. If an object just flies past a planet, it will usually just keep on going, its path bent by gravity, but not captured. For a successful capture, the incoming object needs to lose some energy. One way an object can lose energy is if there's a third body involved. For example, if Triton was part of a binary system, two objects orbiting each other, when it encountered Neptune, the interaction could have ejected its partner, allowing Triton to lose energy and be captured. Another possibility involves gas drag. In the early solar system, the giant planets might have been surrounded by extended envelopes of gas. If Triton passed through such a gaseous envelope around Neptune, it would have experienced friction, like an airplane flying through air. This friction would slow Triton down, causing it to lose orbital energy, and allowing Neptune's gravity to trap it. Section 6. Gravity's Ballet Shaping Orbits and Moons. Gravity is the unseen choreographer of the cosmos. It dictates how stars form, how planets orbit, and how moons dance around their parent worlds. In Neptune's system, gravity has played a particularly dramatic role in shaping the orbits and even the very nature of its moons. The story of Triton's capture is a prime example of gravity's power to rearrange an entire planetary system. Its arrival didn't just add a moon, it likely cleared out or significantly altered the orbits of many others. Once captured, Triton's orbit would not have immediately been the relatively circular, though retrograde, path it has today. It likely started in a very eccentric, elongated orbit much like Nereid's current path. Over millions of years, tidal interactions between Neptune and Triton would have gradually circularized Triton's orbit. This process involves a transfer of energy. Neptune's gravity would raise tides on Triton and Triton's gravity would raise tides on Neptune. This constant push and pull slowly bled energy from Triton's orbit, making it less eccentric and more circular over eons. Section 7. Neptune's Inner Guard, the regular satellites. While Triton and Nereid with their dramatic capture stories often steal the spotlight, Neptune also possesses a retinue of smaller inner moons. These moons are quite different from their larger, more eccentric siblings. They are what we call regular satellites. This means they orbit relatively close to Neptune, their paths are nearly circular, and they orbit in the plane of Neptune's equator, moving in the same direction as the planet's rotation. These characteristics strongly suggest they formed in place from a disk of material around Neptune. These inner moons are all quite small, rocky bodies, and they orbit very close to Neptune, some even within its faint ring system. Names like Naiad, Thalassa, Despina, Galatea, Larissa, S2004N1, now named Hippocamp, and Proteus make up this inner family. Proteus is the largest of this group and is irregularly shaped, looking somewhat like a lumpy potato. It's so dark that it reflects very little sunlight, making it difficult to study from Earth. These moons are like Neptune's personal bodyguards, circling close to the planet. Each little moon has a story to tell about the ongoing evolution of this distant system. Section 8. Windows to the Past. Why these moons matter. Studying Neptune's moons, from Triton to Hippocamp, isn't just cataloging celestial objects. These moons are time capsules offering insights into our solar system's history. Neptune's distance from the Sun means its system is less affected by solar radiation. This makes it more representative of the primordial solar system. Triton, a captured Kuiper Belt object, is particularly significant. The Kuiper Belt is a reservoir of ancient, icy bodies. Studying Triton reveals the composition and geology of these distant objects. This helps us understand the building blocks of the outer planets. Triton is a KBO delivered to Neptune's doorstep for study. The chaotic orbits of Neptune's moons reveal early solar system upheaval. Data from these moons refines our models of planetary system formation. Section 9. Neptune's Enduring Mysteries, a Family of Wonders. Neptune and its diverse family of moons continue to be a source of wonder and scientific inquiry. From the backward-orbiting giant Triton to the eccentric Nereid and the small irregular moons, this system is a natural laboratory for studying cosmic captures and gravitational dynamics. Each moon holds a piece of the puzzle, helping us understand Neptune's history and our solar system's formation. Many questions still remain. What was the exact mechanism of Triton's capture? Was it a binary KBO interaction, or did gas drag play the primary role? What happened to Neptune's original family of moons when Triton arrived? Are the current inner moons survivors, or are they second-generation objects formed from the debris of that cataclysmic event? And what powers the ongoing geological activity on Triton, so far from the sun's warmth? These are the questions that drive future missions and further research. Future missions to the Neptune system, though challenging due to the immense distance, would be incredibly rewarding. An orbiter could study Triton in detail, map Nereid's surface, and investigate the smaller moons and rings. Such a mission could potentially even carry a lander for Triton, allowing us to analyze its icy surface and plumes directly. The discoveries awaiting us in this cold, distant realm could revolutionize our understanding of outer planet systems and the prevalence of dynamic, icy worlds throughout the galaxy. Ultimately, Neptune's moons remind us that our solar system is a complex and fascinating place, still full of surprises. They show us that planetary systems are not static but are constantly evolving under the influence of gravity and occasional cosmic violence. The story of Neptune's moons is a story of cosmic immigrants, survivors, and the powerful forces that shape their destinies. As we continue to explore the universe, these distant icy companions of the blue giant will undoubtedly continue to teach us profound lessons about our place in the cosmos.